Lesson L016, AI Technical Foundations. Welcome to Lesson 16, where we explore the technical foundations that power modern artificial intelligence. This lesson covers neural networks, backpropagation, transformers, GPU computing, model compression, and evaluation metrics. By the end of this session, you will understand how the core technologies behind tools like ChatGPT and Midjourney actually work under the hood. Let us begin with neural networks. At their simplest, neural networks are computational systems inspired by the biological brain, though the comparison is more metaphorical than literal. A neural network consists of layers of interconnected nodes called neurons. Each neuron receives input, performs a simple mathematical operation, and passes the result to the next layer. The architecture typically includes an input layer, one or more hidden layers, and an output layer. Each connection between neurons carries a weight, which is a number that determines the strength of that connection. Each neuron also has a bias, which allows it to shift its activation threshold. When data enters the network, it flows through these weighted connections, and each neuron applies an activation function to determine whether it should fire. Common activation functions include ReLU, which outputs the input directly if positive or 0 otherwise, and sigmoid, which squashes values into a range between 0 and 1. For example, a neural network trained to recognize handwritten digits might take a 28 by 28 pixel image as input, which gives 784 input neurons. It might pass through two hidden layers of 128 neurons each, and finally reach an output layer of 10 neurons, one for each digit from 0 to 9. The network learns by adjusting the weights and biases across millions of training examples until its predictions become accurate. Neural networks come in many specialized architectures. Convolutional neural networks, or CNNs, are designed for processing grid-like data such as images and use convolutional filters that scan across the input to detect patterns like edges, textures, and shapes. Recurrent neural networks, or RNNs, were designed for sequential data like text or time series and maintain a hidden state that carries information across time steps. While CNNs and RNNs dominated their respective domains for years, both have been largely superseded by transformer-based architectures in most modern applications. Now let us examine backpropagation, which is the mechanism by which neural networks actually learn from their mistakes. Backpropagation, short for backward propagation of errors, is the algorithm used to calculate the gradient of the loss function with respect to each weight in the network. The process begins with a forward pass, where input data travels through the network and produces a prediction. The prediction is then compared to the true label using a loss function. For classification tasks, cross-entropy loss is common, while for regression tasks, mean squared error is typical. Suppose the network predicts a 7 when the correct answer is a 3. The loss function produces a large error value. Backpropagation then calculates how much each weight contributed to that error by applying the chain rule from calculus, working backward from the output layer through the hidden layers to the input layer. Once these gradients are computed, the optimization algorithm, typically stochastic gradient descent or one of its variants like ATOM, updates each weight in the direction that reduces the loss. The learning rate controls how large these updates are. A learning rate that is too high can cause the network to overshoot the optimal values, while a rate that is too low leads to painfully slow training. One full pass through the entire training dataset is called an epoch, and modern models often train for dozens or hundreds of epochs. It is remarkable to consider that networks with hundreds of billions of parameters are trained using this same fundamental algorithm, just scaled across thousands of computers. Transformers represent the most significant architectural breakthrough in AI over the past decade. Introduced in the landmark 2017 paper Attention Is All You Need by Vaswani and colleagues at Google, the transformer architecture replaced the recurrent and convolutional layers that previously dominated natural language processing. The core innovation of the transformer is the attention mechanism, which allows the model to dynamically weigh the importance of different parts of the input when producing each part of the output. Consider the sentence, "The cat sat on the mat because it was tired." The word "it" refers to the cat, not the mat. An attention mechanism can learn to connect it to cat by computing attention scores between every pair of words in the sequence. Transformers use a specific form called self-attention, where each token in the input attends to every other token. The mechanism works by creating three vectors for each token: a query, a key, and a value. The query from one token is compared against the keys from all other tokens using a dot product, producing attention scores. These scores are normalized using a softmax function, and the resulting weights are used to compute a weighted sum of the value vectors. This allows each token to gather context from the entire sequence. Transformers also employ multi-head attention, which runs multiple attention operations in parallel, each learning different relationships. The architecture additionally includes positional encodings to give the model information about word order, and feed-forward layers that process each position independently. The original transformer had an encoder-decoder structure, but modern variants like BERT use only the encoder for understanding tasks, while GPT models use only the decoder for generation tasks. GPT-3, released in 2020, had 175 billion parameters and was trained on approximately 500 billion tokens of text. The scaling of transformers has led to the phenomenon of emergent abilities, where models suddenly become capable of tasks they were not explicitly trained on once they reach a certain scale. GPU computing has been instrumental in making large-scale AI training feasible. Graphics processing units, or GPUs, were originally designed for rendering graphics in video games, but their architecture turns out to be ideally suited for neural network computations. A CPU is designed for sequential tasks and contains a few powerful cores optimized for low-latency operations. A GPU, by contrast, contains thousands of smaller cores designed for parallel processing. Neural network training involves massive amounts of matrix multiplication, where each layer computes the product of the input vector and the weight matrix. These operations are embarrassingly parallel, meaning they can be split across thousands of cores simultaneously. For example, NVIDIA's A100 GPU has 6,912 CUDA cores and can achieve 19.5 teraflops of single-precision performance. Training a model like GPT-3 required approximately 3,464 A100 GPUs running continuously for several weeks. The total computational cost was estimated at around $4.6 million just for the final training run, not including research and development costs. The demand for GPU computing has become so intense that it has created global shortages, with lead times for enterprise GPU orders stretching to over a year in some cases. Companies like NVIDIA have seen their valuations skyrocket as a result, surpassing $1 trillion in 2023. There are ongoing efforts to develop AI-specific hardware, including Google's Tensor Processing Units or TPUs, which are custom ASICs designed specifically for tensor operations, and various startups working on novel architectures for AI acceleration. Model compression addresses the practical challenge of deploying these massive models in real-world applications. A state-of-the-art language model might require hundreds of gigabytes of memory and significant computational resources for each inference. This is impractical for running on a smartphone, a web browser, or an edge device. Model compression encompasses several techniques to reduce model size while preserving accuracy. The first technique is pruning, which involves removing unnecessary connections or even entire neurons from the network. Research has shown that many neural networks are significantly over-parameterized, and up to 90% of the weights can be removed without substantial loss in accuracy. Magnitude-based pruning simply removes weights with the smallest absolute values, assuming they contribute least to the output. Structured pruning removes entire channels or layers, which is more compatible with hardware acceleration. The second technique is quantization, which reduces the precision of the numbers used to represent weights and activations. While training is typically done in 32-bit floating-point precision, inference can often be performed using 16-bit, 8-bit, or even 4-bit integers. This reduces memory usage by 4 to 8 times and can dramatically accelerate inference on specialized hardware. The third technique is knowledge distillation, where a smaller student model is trained to mimic the behavior of a larger teacher model. The student learns not just from the ground truth labels but from the probability distribution produced by the teacher, which contains rich information about similarities between classes. For example, when training a student model to classify animals, the teacher might assign a probability of 0.8 to dog, 0.15 to wolf, and 0.05 to cat. The student model learns from this soft distribution rather than the hard label dog. This often results in a much smaller model that achieves accuracy close to the larger model. DistillBERT, a distilled version of BERT, retains 97% of BERT's language understanding while being 40% smaller and 60% faster. Evaluation metrics are how we measure whether our models actually work as intended. The choice of metric depends heavily on the task. For classification tasks, the simplest metric is accuracy, which is the percentage of correct predictions out of total predictions. However, accuracy can be misleading when classes are imbalanced. If a medical dataset has 99% healthy patients and 1% sick patients, a model that always predicts healthy achieves 99% accuracy but is completely useless. This is where precision, recall, and F1 score become essential. Precision measures what proportion of positive identifications were actually correct. If the model flags 10 patients as sick and 9 are actually sick, precision is 90%. Recall measures what proportion of actual positives were correctly identified. If there are 10 sick patients in the dataset and the model finds 9, recall is 90%. The F1 score is the harmonic mean of precision and recall, providing a single number that